Bismillahirrahmanirrahim. Construct the Bode plots for the transfer function. H of omega is equal to 200 j omega divided by j omega plus 2 into j omega plus 10. So the Bode plots comprise of two parts, the magnitude plot and the phase plot. So to plot the Bode plots, we need to first transform this given transfer function into the standard form. So we can sometimes replace j omega with s for ease of manipulation, or we can leave it as it is, but we first transform this in the form of these terms must be 1 plus j omega over, for example, p here, p for pole, and the upper terms will be 1 plus j omega over z, z for 0. If these are linear terms, right? So h of omega is 200 j omega at the numerator, and we have this j omega plus 2 would take 2 common here, and we take out 10 common from here. So this is 2 and this is 10 common from the other term, so this will become 1 plus j omega over 2, 1 plus j omega over 2, and this will become 1 plus j omega over 10. So now these are in the standard form, but this constant term, this is then 20, so 200 divided by 20 leaves us with 10 j omega, and now this is 1 plus j omega over 2 into 1 plus j omega over 10. So we have 1 0 at the origin, and we have a pole at 2 and we have a pole at 10. So these are our corner frequencies. So for the magnitude and phase plot, let's write this in polar form. So for example, h of omega is 10, this is the magnitude of j omega, divided by 1 plus j omega over 2, the magnitude, and then 1 plus j omega over 10, the magnitude, and then the phase angle here. So this j omega term causes 90 degrees, right? And this constant term causes 0 degrees only. So this is 90 degree, and minus we have tan inverse omega over 2. This minus because this is in the denominator and this is the pole, and then minus tan inverse omega over 10. So this gives us the magnitude and this gives us the phase plot, but the magnitude is to be transformed into dB. So HdB, 20 log h, so the 20 log 10 plus 20 log of this term j omega, and then minus 20 log, minus because this is for the poles in the denominator, 1 plus j omega over 2, and minus 20 log 1 plus j omega over 10. So and the phase angle, phase angle will be 90 degree minus tan inverse omega over 2 minus tan inverse omega over 10. So the magnitude plot comprises of 1, 2, 3 and 4 terms, 4 asymptotes. 4 asymptotes will combine together to give us the magnitude Bode plot, and these are the 3 terms in the phase plot for the Bode plot. So the Bode plots are plotted on semi-log paper. So here is a semi-log paper. Why this is called semi-log? Because as you see, the vertical lines, the space between them is not uniform. It follows a logarithmic pattern, and the horizontal lines, however, there is a uniform space between them. So if the horizontal lines also are like the vertical lines, so this will then become a log paper, because only vertical lines follow a logarithmic pattern and horizontal lines have uniform spaces. This is called a semi-log paper. So the Bode plots are plotted on a semi-log paper, and because we need to see the response over a wide range of frequencies, so using logarithm we can follow a wide range of frequencies. Let me just draw a horizontal axis here for the magnitude plot, right? This is omega, right? Omega in radians per second, and this is the vertical line for the magnitude plot. So this is HdB here, HdB. So this is, for example, 0 dB, and this is 20 dB, and this is minus 20 dB. And the horizontal axis follows a logarithmic scale. So for example, this is 10 raised power minus 2, 10 power minus 2, or 1 over 10 power 2, that is 1 over 100. This is, for example, 10 power minus 1. This is 10 power 0. So that is 1. And this is then 10 power 1. And this is then 10 power 2, 10 power 3, and so on. So this is 0.01, this is 0.1, this is 1, this is 10, this is 100, and this is 1000. So if we multiply the previous term with 10, we get the next interval, right? And also the space between these small blocks is, for example, this is 10 and this is 100, then this is 10, this is 20. Then this is 30, 40, 50, 60, and so on. And this is 100, this is 200, 300, 400, so on. This is 1000. So this is how it goes. So we have first constant term. So the constant term is 20 log 10. So 20 log 10 is 1. 20 into 1, that is 20 dB. 20 dB. So first term is constant, 20 dB, right? So let me just draw a line for 20 dB here. So this is 20 dB, right? 20 dB line. So one term, and the next term is 20 log j omega. So this is a straight line with a slope of 20 dB per decade, and it is 0 at omega is equal to 1. So this is 10 power 0, and this is basically 10 power 0 is 1. So this is here, and it is 20 dB per decade. So this is 1 decade, for example. So this is 1 and this is 10, right? The difference between them, if you divide both of them, is 10, and the consecutive difference between them also is 10. So this is 1 decade, and 20 dB is this distance, right? So this here, from here to here, this is 20, difference is 20 dB. So difference between this point here and this point is also is 20 dB. So this is 20 dB per decade. So for example, it is 0 here. So after 1 decade, it should be 20 dB, right? So this is this is 20, and here, this point here, and this point here. So the line joining all these points will give us the asymptote for j omega, right? So this line, this represents 20 log 10, and this line now represents 20 log j omega, right? 20 log j omega. And the next line is this was a constant term, this was simple 0, and we now have a pole at omega is equal to 2. So this is 10 to the power 0 is 1, so this is 2 here, right? So at 2 we have a simple pole, right? So it is 0 from here till here till 2, the line, this is 0, right? The asymptote is 0 till this corner frequency. This is the corner frequency, and then this has a slope of minus 20 dB per decade. So minus 20 dB per decade, so this begins, this is 2 here, so at 20 this will be 20, so at 20 this should be 20 dB here, right? 20 dB, so this is minus 20, so this is minus 20 here, right, after 1 decade. So this gives us this line. So this line here is for this asymptote 20 log 1 plus j omega over 2, 1 plus j omega over 2, right? And then we have another term, asymptote at omega is equal to 10. So omega is equal to 10, this term here, and at this line also the asymptote is 0 till this point, it is 0 this till this point, and from now this onwards it has a slope of minus 20 dB per decade. So 1 decade will become here, so this is the next decade, and the 20 dB is at this point, right? Minus 20 dB. So this gives us another asymptote at minus 20 dB per decade, right? So we have plotted all the 4 asymptotes, the constant term, the j omega term, j omega over 2 and j omega over 10 asymptotes. We need to sum them all together. You see here they are all additions or subtractions, and this gives us the HDB. So we need to sum them all together to find the constant to find the composite plot, the resultant plot. So if you see, if we can extend this line, this is minus 20 dB here, and here it will be minus 40, and at this point it should extend to this line here, right? So it extends till here. It is minus 40 here. This is minus 40, but this term is plus 20. So the resultant at this point at 10 to the power minus 2 is 20 minus 40 is minus 20. So we get 1 point here at minus 20 dB. But at this point, this is minus 20 and this is plus 20. So this will 0, right? The next point is 0. So we get a line parallel to this line. So it will go on like this till we get a corner frequency. So the corner frequency is here, where we get the third asymptote. When we add the third asymptote, it will change. So till this point, we draw a straight line, right? So it is at this point. So till this point, we get a straight line like this. Let me draw it with black, the resultant plot. So this is this line, 20 dB per decade. And then next we get at this corner frequency, we get a minus 20 dB per decade added to the previous 2 asymptotes. So this minus 20 dB per decade will cancel out this positive slope, and this will become a horizontal line till the next asymptote, till here, right? So this will be a horizontal line till here, till the next asymptote. And at this corner frequency, we have another minus 20 dB per decade. So this will again deflect this composite plot to minus 20 dB per decade. So this is this will be a horizontal line parallel to this one, right? So this will be this plot. So then this is the resultant plot now, resultant magnitude plot, right? So adding the four plots together, we get the resultant plot. And note one more thing, this is an approximate plot. This is approximate or asymptotic plot. Asymptotic plot or approximate plot. For example, note that at the corner frequency, the value of the asymptote is 0. But let's look at the actual case. For example, at omega is equal to 2, the corner frequency, when omega becomes 2, what will be the actual value? We have shown a 0 here, right? 0 dB here at omega is equal to 2. But when omega is equal to 2, for example, so this becomes minus 20 log 1 plus j omega 2 and divided by 2, this is 1, right? So j 1 plus j1. So what is minus 20 logs is the magnitude of 1 square plus 1 square square root. So that is minus 20 log. So this is 2 square root, right? So 20 log 2 square root is approximately 3. So this is 3 dB, minus 3 dB. So the value here should be minus 3, but we use here 0, right? The asymptote value is minus 3 here. And similarly, for if we have a 0, so the value would be plus 3 dB at that point. So what we can do is we can use this approximation. So for example, if this small block is 4 dB, so the actual value will be 3 dB less. So it will be something like here, right? And similarly for this, it will be something like here, right? So we can use approximation like this to construct this plot. Maybe it can go on to the peak and then come back, right? So this is the exact plot. Then again an approximation, but closer to the exact plot. So this is the asymptotic plot, and if we apply this 3 dB correction, so then this will be the better approximation or closer to the exact plot. So this was the magnitude plot. Similarly, we can plot the phase plot as well, Bode phase plot. So we have 3 terms, so we can plot them together individually, and then put them together to find out the composite phase plot. So let me draw simply a horizontal axis again here. So this is omega in radians per second, and the vertical axis will be for the phase angle, vertical axis for the phase angle. So this is phi, and this is times power, for example, minus 2 again. This is times power minus 1. This is times power 0. This is times power 1. This is times power 2. This is times power 3, right? So let's plot the individual terms now. So first we have a 90 degree. So suppose we have this is 90 degree, right? At this point we have, this is phase angle, so we have 90 degree here, right? Plus 90 degree here, and we have, and minus 90 degree here, minus 90 degree here, right? So the 90 degree term we gives us a constant line here at this point, so this is 90 degree. And then we have omega is equal to 2. So omega is equal to 2 gives us minus, this is the pole, so minus 40 degrees per decade. We have a line at minus 40 degrees per decade, but for example, let's call this carrier corner frequency 1, that is 2 radians per second. So at 0.1 omega C1, and that is basically 0.1 multiplied by 2 is 0.2 radians per second. It will be 0 till this point, right? And from this onward, it will have a slope of minus 40 degrees per decade till 10 omega C1. So that is 20 radians per second. So till 20 radians per second, from 0.2 to 20 radians per second, it will have the slope of minus 40 degrees per decade, and from this onwards, it will be constant at minus 90 degrees. Minus 45 degrees per decade slope, and then constant at minus 90 degrees. So let's begin at 0.2 radians per second. So this is 10 to the power minus 1. So this is basically 1 over 10. This is 0.1, and this is 0.2, right? This is 0.2. So it is 0 till here, and then from 0.2 to 20. So this is 10 and this is 20, right? Till 20, it has a slope of minus 45 degrees. So this is 45 is here per decade, and 2 decades will give us, these are basically 2 decades, so this will give us 90 degrees. So till here it has a slope of minus 45 degrees per decade, and at this line, at this point, it becomes constant at minus 90 degree, right? So this is minus 90 degree. So this is 90 degrees. Then this is tan inverse minus tan inverse omega over 2, right? And minus tan inverse omega over 2. Then we have omega is equal to 10. So at omega is equal to 10, let's call this corner frequency 2 is 10 radians per second. So at 0.1 omega C2, it will be 1 radian per second. So till this point it will be 0, and till 10 omega C2, so that will be 100 radians per second. So till 100 radians per second, it will have a slope of minus 45 degrees per decade, and from that point onwards it will be minus 90 degrees. So we begin at 0.1 omega C2, this is 1 radian. So at 10 to the power 0, so this is 1 radian, right? And till 100 radians per second, right? This is 100 at this point, right? So till this point, it has the same slope as this line, starting from this 10 raised to the power 0. So this is this gives us minus 45 degrees per decade, and then again this is constant at minus 90 degrees, right? So this was actually omega minus tan inverse omega over 2, and this line is minus tan inverse omega over 10. So now we can combine all these plots together to find out the constant, the composite plot. So we begin at 90 degrees at till this break frequency, right? So till this break frequency, this is the first, this frequency here. So till this point, we have this constant line, right? So it is 90 degrees, and then it has a slope of minus 45 degrees per decade, line parallel to this line till this point, right? Till this frequency. So it is a line parallel to this till this point, right? And from this point onwards, it has a slope of minus 45 and minus 40, minus 90 degrees per decade. The slope becomes steeper till this point, right? Till this point, right? Because after this slope minus 45 degrees is no longer there. So we have this line, a slope like this till here, and then again it follows a slope of 45, minus 45, which is along this line at this point, and then it straightens out at minus 90 degrees per decade again, because you see this is plus 90 and there are two minus 90s here. So plus 90 and one minus 90 cancel out and we get balance of minus 90 degrees at this point, right? Similarly, at each point we can see that let me summarize it again. So this start with the 90 degrees here, because there is no other term from this point till this point, and from this point onwards till this point we have two terms, one 90 degree and one minus 45 degrees per decade. So from this point onward till this point, till the next term adds to the previous terms, the slope is minus 45 degrees per decade. At this point, the next term is added together. So this is minus 45, this is also minus 45. The slope becomes steeper, which is minus 90 degrees. And this goes on till this point, because at this point, this term, the slope goes away and we have a constant term at minus 90. So the slope becomes again minus 45 degrees, right? So minus 45 degrees slope, and at this point again we have this term plus 90 and minus 90 and minus 90. So this straightens out at minus 90 degrees. So this is the resultant plot. And this resultant plot is also approximation. We can apply a correction similar to this one here. So this is again something, a curve like this, a curve like this. It begins it here and then it goes on like this. So so these are the Bode phase and magnitude plots, which given the transfer function we can draw the Bode magnitude and phase plot by first converting it to the standard form. And one more thing, given the magnitude plot, for example, we can infer the transfer function from the magnitude plot. For example, let's forget what the transfer function we were given. Let's just look at this this asymptotic plot, this composite plot here, this composite plot. So from the composite plot, we can infer the corner frequencies and then figure out whether this corner frequency is a zero or a pole, and then we can put together a transfer function in the standard form. And from that standard form, we can convert into a proper form to arrive at the transfer function. So, for example, Let's look at this magnitude plot. For example, we have this straight line here, right? And this straight line goes on from minus 20, crosses till 10 power minus 0, and this goes on till here, and this flattens out here. So at this point we have a corner frequency, right? At the corners where where the plot changes its direction, we have a corner frequency. So this is 10 raised power 0, and this is 1, and this is 2. So we have a corner frequency, for example, omega c1 at 2, right? Similarly, we have a corner frequency here, because it changes direction. The composite plot changes direction. It has a corner frequency of omega c2 is equal to 10 at 10 power 1, which is 10 radians per second. So we have two corner frequencies at 2 and 10. So how do we know that these are poles or zeros? So if we look, this slope was positive. So this then flattened out. Instead of going upwards or taking a more steeper slope in the positive direction, it just cancelled out and is now in the horizontal direction. So this is a pole here. Again here, this is a pole. So this is 1 plus j omega over 2 term, right? And this is 1 plus j omega over 10 term. So we can mistake this line to be a 0 in the form of with a corner frequency at 10 to the power minus 1. But 10 to the power minus 1 is not a corner frequency, because it is going on in the same direction and it is crossing this horizontal axis like this. So this term is basically a 0 at the origin, because the horizontal, this line, straight line crossing the horizontal axis results in shows a simple 0 at the origin. So we have a 0 at the origin also. So j omega term. And but this 0 is only, the 0 only crosses the horizontal axis at 10 power 0, like this line here, but this is crossing it here. So it means that we have a DC component added to the 0. So if we look at it should be 0 actually at this point, right? But this has a value of 20 dB at 10 power 0 at 1. So instead of being 0 at this point, so this is 20 dB. So the k term is basically, if it was k term, is 20 log k is 20 dB here. So this is 20 dB, whatever value. If it was 40, I would write 40 here. So from this we can find out the value of k, the constant term. So basically this is log k is equal to 1. So k log inverse 1 is 10. Log 10 is basically log of 10 to the base 10 is 1, and the log inverse of 1 is 10. So this is 10. So k is equal to 10. So having found out all these values, we can put together our transfer function. H of omega is k is 10. Then we have a simple, we have a 0 at the origin, 10 j omega, and we have a pole 1 plus j omega over 2, and we have a pole plus 1 over j omega over 10. So we can write this 10 j omega, and we can take the LCM as 2. So this is 2 plus j omega, right? And the 2 term comes here, right? And we can just write it 10 plus j omega, take the LCM, and the 10 term comes here. So h of omega becomes, this is 200 j omega divided by 2 plus j omega into 10 plus j omega. So given the magnitude plot, for example, we can infer the transfer function. This is the same transfer function that we will already provided with. So this transfer function we were given, and we have found out the transfer function from the magnitude plot. So given the magnitude plot alone, the composite plot, we can figure out the transfer function as well, knowing the corner frequencies, noting down the corner frequencies, right? So with the help of the corner frequencies, we can find out the transfer function from the magnitude plot as well.